Hey there, my name is Tom O'Sullivan and I'm an assistant professor of electrical engineering and the bioengineering graduate program here at the University of Notre Dame. In other words, I typically mentor PhD students who are studying toward a PhD in electrical engineering as well as bioengineering. And I'd like to spend the next couple of minutes telling you a little bit about what my lab does here. We study the interaction of light with living biological cells and tissues, and we like to use the knowledge of those interactions to apply them to applications and techniques that are used to understand, diagnose, and even treat disease. Now, when you think of that, that area is broadly called biophotonics. Most people think of microscopy. And really, this is probably the earliest and pervasive use of light for diagnosing disease today. But it turns out this is not what I do. My work is about safely extracting physiological information from deep within human tissue. But if you are interested in microscopy, in particular super resolution imaging, and creating instruments and developing new applications for these technologies, I encourage you to check out the work of my colleague, Professor Scott Howard, also in the Department of Electrical Engineering and the Bioengineering Graduate Program. Professor Howard is a frequent collaborator of mine, and his lab develops these new instrumentation to do deeper tissue, super resolution chemical and molecular imaging, and you can see here some of the beautiful data his lab has collected. But back to me, what I do is not as much like that, where Professor Howard goes super high resolution, but relatively shallow in tissue. I try to extract information from deep in tissue, but of course the trade-off is we don't get as high of a resolution image due to how light interacts and scatters through tissue. This is close to what you probably have seen before, called a pulse oximeter. So this device uses light in your finger or your toes to measure how much blood in your arteries is oxygenated. And of course, has become a very important tool for diagnosing a cardiovascular disease or respiratory illnesses. You can take that a step further and try to use that type of technique to measure oxygenation in the brain. And in fact, many devices such as these can be found in many neonatal intensive care units throughout the country. And this is closer to what my lab does. And we've used this type of technique, broadly called diffuse optical spectroscopy, for neuroimaging, for studying the brain and trying to identify which parts of the brain are working at a particular point in time. We do a lot of work in breast cancer using these techniques to study breast tumors, identify characteristics that mean they are aggressive, they are growing, or in particular are responding to treatment. We also look at lactation health in general. To see how well the human breast is producing milk. In breast cancer, you can see an example of that here on the next image, where we've imaged a woman with the technology we've created in my lab, a woman who has breast cancer, and we're looking at that tumor and trying to understand certain characteristics about that. We are very sensitive to blood in the tissue, and you can see here, a few years ago, I broke my foot, and I went to the lab and asked one of my students to take a picture of my feet with one of the technologies we work with, and you can see clearly which foot is broken. It's the one on the left side in the image here. And you can see very clearly all of that soft tissue damage and blood underneath the skin. So my lab is all about developing and applying this technique of diffuse optical spectroscopy. And here's just a sampling of some active research projects we have going on in the lab right now. One is applying these in breast cancer. In particular, we have 2 human clinical studies going on right now. We are trying to use our technology to determine whether breast lumps or breast masses are likely to be cancer or more normal or benign. And we do that here in South Bend at one of the local hospitals, St. Joseph Medical Center, as well as with our collaborators over in New York at Northwell Health. We also develop new technologies in order to create these types of images. So as electrical engineers, one of the things we do is create new ways, better ways, faster ways, more power efficient ways to take these types of measurements. And we're funded generously by the NIH to keep pursuing this work. So we develop and apply electronic and optoelectronic components and devices into creating real systems that we also put into those clinical studies, which I already mentioned. Here's an example of one of those projects. This is a handheld breast scanner that we've developed that we are now translating out into the world through the creation of a startup company that was co-founded by myself and one of my students. Besides breast cancer, as I mentioned, we look at lactation health. We've looked at biomarkers of malaria infection, and we have a new study we're excited that's starting in the next year to look at opioid withdrawal in babies and newborn babies. So these are babies whose mothers, unfortunately, were addicted to opioids or pain medication, and there's quite a bit of uncertainty in the clinic now of how to treat those babies. If they start showing withdrawal symptoms, how do you identify that and treat that? And we've got a study with some great collaborators down at Indiana University in order to apply the techniques we develop here in order to better understand that. Now, all of that I've mentioned is actually one half of my lab. The other half of my lab looks at taking these technologies and creating implantable devices. So we take these components that we use for imaging, light sources and detectors, and we make them into really small capsules about the size of a grain of rice that we can inject into the body and use it to interrogate tumors, for example, from within. Now, of course, you have to do this all wirelessly, so we rely on great collaborations we have with faculty who do wireless communications and integrated circuits in order to achieve the size that we need in order to do this type of sensing. So if you're interested in my work here at the University of Notre Dame or any of my colleagues in the bioengineering graduate program, I invite you to contact us. You can see my email at the bottom of each of these slides, so don't hesitate to reach out. And I'd like to thank all of my past students, you can see on the list here, and our collaborators who's contributed to this work. And we look forward to hearing from you soon.